Hello, my name is Herbert Alexander Santana de Bruin, and today I'll be discussing my paper, which is Residual Cnn-Gru networks for intrusion detection systems, which is a tiny reproduction of the original paper, which is Pelican, a deep residual network for network intrusion detection. And for the sake of it actually being a tiny reproduction, I'll only be approaching one of the claims that they discuss on the paper, which is for fixed depth, residual networks outperform plain networks on accuracy, detection rate, and false alarm rate. And I'll also only be analyzing one of the architectures, the shallow one that they discussed, that's the plain 21, the residual 21, as well as a five-fold cross-validation instead of a 10-fold cross-validation. So the first thing I'm going to discuss the actual architecture they're going to use. As you can see here in this image, you have the A, the plain block, and B, the residual block, and both blocks applies batch normalization followed by a convolution on 1D layer with relocation, max pooling, another batch normalization layer with a groove cell, then reshaping and dropout. And the same happens for residual, but with a skip connection between the batch normalization first layer and the final block. And for us, since we're doing a residual 21 and a plain 21, we need to stack 5 of these blocks for each of them. And as we discussed, the data set will be the NSL-KDD, which is about 148K samples. And the pre-processing will happen with one hot encoding that will expand the features to 122. And each feature will be standardized to have a 0 mean and 1 standard deviation. And this standardization will happen per fold. And we'll have a binary labeling with normal being 0, attack being 1. Both filters use 122 filters, 10 kernel size, 120 Gru units, and 0.6 dropout. As well as on the training side, we have a 4,000 batch size, 50 epochs, early stopping, graded clipping, and also RMS prop optimizer with 0.01 learning rate. What we had after training model, I'm able to conclude that the residual network does outperform plain deep models for intrusion detection on ANSL-KDD. As you can see here, the green residual training here, it starts lower and goes lower, it stabilizes the lower loss. This which does not happen for the Pelican training blue here, and the same trend happens for both residual validation and plain validation. On the other hand, here on the original paper graphs, even though their values are better, like in terms of absolute value, it does follow the same trend with the residual 21 here beneath this red one being lower than the plain 21 for training loss. The same happens here for the plain 21 here and the residual 21 here, the residual 21 lower there. Then discussing for the results, we have that the plain 21, the residual 21 significantly outperforms plain 21 by 14% on accuracy, 14.1% on accuracy, 20.61% on the detection rate, and 8.06% in false alarm rate. However, the best overall model was one of the basic classical baselines, which is the LMLP, that he reached a higher absolute accuracy on this tabular data set, which is good. But overall, it was higher than expected. But overall, we were still able to confirm the Pelican's architecture insight, which is residual Cnn-Gru networks outperform plain deep models, and that the skip connections improved optimization, stability, and final performance by, as we showed before. The residual 21 showed substantial gains over plain 21 in all metrics analyzed. Thank you everyone for coming. It was my pleasure to present you this, and bye.